आज हमारे टॉप 12 करेंगे बैचेस
के जो हाथ न आए वो इनाम
बैगिंग उस लेवल पे नहीं था जिस लेवल पे आप लोगों का परफॉर्मेंस।
सुन मेरा असल बोलते इसको
Anthony, has the resource person joined?
Hello.
Yes. You can take it, not check time. It's about to start.
Hello. Bedansila, now you start.
Please open.
Hello.
Okay, ma'am.
Okay, thank you.
Good morning, participants. I am Benangchila. I'm going to be the moderator for today. I am an assistant professor in Department of Electronics and Communication, School of Engineering, Nagaland University. So, the third session, welcome to the third session, third day. So, for our first session, today we have Professor Bilas Pachori. So, let me give a brief introduction about our esteemed guest. Professor Bilas Pachori received his BE degree with honors in Electronics and Communication Engineering from Rajiv Gandhi Technological University, Bhopal, India in the year 2001, and his MTech and PhD degrees in Electrical Engineering from IIT Kanpur in the year 2003 and 2008 respectively. Before joining IIT Indore, he worked as a postdoctoral fellowship at Charles Delaunay Institute, University of Technology of Troyes, France, in the year 2007 and 8, and an assistant professor at Communication Research Center, International Institute of Information Technology, Hyderabad, from 2008 to 2009. He served as an assistant professor and an associate professor at the Department of Electrical Engineering, IIT Indore, and presently he is working as a professor at the Department of Electrical Engineering, IIT Indore from 2017. Currently, he is also associated with the Center for Advanced Electronics at IIT Indore. He has served as visiting professors at various universities outside India, namely, he served as a visiting professor in Department of Computer Engineering, Modeling, Electronics and System Engineering at the University of Calabria in Italy in July 2023. Also as a faculty of Information and Technology in Communication Technology, University of Malta from June to July 2023, and in Neurodynamics of Visual Cognition Lab, Free University of Berlin, Germany, from July to September 2022. School of Medicine, Faculty of Health and Medical Science, Taylor's University, Malaysia, 2018 to 2019. Previously, he worked as a visiting scholar at Intelligent Systems Research Centre, Ulster University, Londonderry, UK during December 2014. His research interests are in the areas of signal and image processing, biomedical signal processing, non-stationary signal processing, speech signal processing, brain computer interfacing, machine learning and artificial intelligence, and Internet of Things in healthcare. He is an associate editor of Electronics Letters, IEEE Transactions on Neural Systems and Rehabilitation Engineering, Biomedical Signal Processing and Control, and an editor of IETE Technical Review Journal. He is a fellow of IETE, IEI, and IET. He has 297 publications, which include 183 journal papers, 78 conference papers, 10 books, and 26 book chapters. He has also 8 patents, 1 from Australia and 7 from India. His publications have been cited approximately 14,500 times with H index of 65 according to Google Scholar. So, Professor, we are very glad that you have accepted our invitation and you have uh, to be a part of this faculty development program. So, without further ado, now I give the time to take up this session. Thank you.
Welcome, sir.
Thank you very much. Thank you very much, madam, for nice introduction. And I would like to convey my thanks to Professor Das for providing this opportunity to be part of this faculty development program and also to deliver this talk. Thank you very much. Let me share my slides.
Thank you, sir. Thank you.
Time to time you check like that. Okay, might no.
Was after it was turned on.
Hindi kalin na speaker la off the body ile mic.
Are you able to see slides?
Mula nam to jazz so video.
Yes.
Yes, sir. Okay, thank you very much. So actually, in this talk, the focus will be on actually the use of signal analysis techniques and machine learning for development of automated systems, expert systems, intelligent systems for diagnosis of heart diseases. So generally, actually, when you go to hospitals and this for the heart diseases diagnosis for treatment, and these doctors actually they record your ECG signal, electrocardiogram signal, and they print it on the paper, and they perform visual scanning. So that process is actually very time consuming, and this machine learning together with signal analysis techniques actually can give us nice framework which is very useful for performing this fast diagnosis. Even like rural areas where we have shortage of doctors, such systems, whatever we design in the form of algorithm, can be implemented as an app or can be implemented as software together with these smartphones, laptop, computing devices, and in that way, actually, this such devices with the help of such software can be used. It is actually very useful for the rural areas where we have shortage of doctors, and also in urban areas where we have a lot of patients and doctors are less. So such actually systems can help actually doctors to perform diagnosis in efficient manner. So due to these reasons, there is a lot of actually interest in the literature to use signal analysis together with machine learning techniques for developing this electrocardiogram signal based data processing for diagnosis of heart diseases. So with this background, let us start this talk. So actually, if you see the motivation for this cardiovascular diseases diagnosis, so this is number one cause of the death, and you must have seen in the daily life in the newspapers every day. We find someone dying due to this cardiovascular diseases, and this is one of the actually the top cause of the death. And every year 17 million people die due to cardiovascular diseases, and the mortality rate due to cardiovascular diseases, if you talk about in India, it is actually 272 persons per 1 lakh people. and if you see globally, it is 235 persons per 1 lakh population. So you see in India actually we have a large number, even higher number than this global level. So this actually India heart diseases are very serious, and it is more number. And the common heart diseases that generally we hear, that is coronary artery disease, myocardial infarction, congestive heart failure, and atrial fibrillation. So in this actually talk, we will see how this machine learning algorithms together with signal processing can be used for the diagnosis of heart diseases and such diseases like CAT, MI, CHF, AF, and for the diagnosis, whenever anyone has heart diseases and they go to hospital, so cardiologists or doctors first record ECG signal. So ECG signal, electrocardiogram, is actually like a signature, and that is actually it is the indication. And quickly when ECG is abnormal, doctors go for further treatment. So this is one of the pre test. It is very useful test for the further treatment. So this computer, this a diagnosis system is required that due to certain reason that I mentioned, if you just use ECG, visually you scan it, then actually it takes a lot of time, and it is actually computationally expensive. Like sometimes we need actually fast processing, and we want to have fast decision based on the ECG. So in such scenario, instead of the visual scanning of the signal, it is better to use this intelligent system, expert systems, so that actually timely they can detect the disease. So the objectives in this actually for this presentation, actually this is based on our previous work, and where we have developed an automated detection method based on the flexible analytic wavelet transform based on heart rate variability signals. So that actually we'll see in this talk. And also the developed automated diagnosis method for coronary artery disease based on the flexible analytic wavelet transform based using ECG signals, that also will be explained. And we have also developed an automated identification system for the myocardial infarction ECG signals based on this flexible analytic wavelet transform framework, that also will be actually presented in this talk. And we have proposed a computer-based approach for the automated diagnosis of congestive heart failure patients based on the flexible analytic wavelet transform using heart rate variability signals, that also we will see in this presentation. In the end, this development of actually computer-aided identification system for atrial fibrillation ECG signals based on the FA, flexible analytic wavelet transform, that also will be explained. So the first part of this talk is automated detection method for normal and coronary artery disease heart rate variability signals based on flexible analytic wavelet transform. So if you see actually this coronary artery disease, it is actually is very common sometimes after some age, like when people cross 70 years age and actually they develop the disease. So here, during this disease, the heart muscles get weaker with time, and it also affect the metabolic activity. And this disease called coronary artery disease may cause arrhythmias and heart failure. So due to these reasons, the timely diagnosis is actually necessary. And you can see right hand side this lipid deposit of plaque in case of coronary artery disease, and due to that this narrows the artery. And this you can see the left hand side normal artery, there is no blockage, there is no lipid deposit of plaque. And when you go for this coronary arteries, then you say this deposit lipid deposit is of plaque is taking place, and due to that it becomes this artery becomes narrow, and it creates the problem for the passing the blood. And also due to that this heart muscles get weaker in time. So it's a very serious disease. And we have proposed this actually framework from the heart rate signals. So in this cardiac signal processing, actually we use two kind of signals generally. One is electrocardiogram signal, and that is one is other one is heart rate variability signal. So this is actually obtained from the ECG, electrocardiogram signal. So if you are in the hospital, you have very good environment where less noise is present, then we go for ECG signal. And if you want to have the recording of the heart signals, and it is in the urban rural areas or some uh, remote areas where actually you have noisy scenario, then we go for heart rate variability signal. So that actually we extract this based from the ECG signal, and that is just based on the R point information, RR interval. So in that way, noise effect is less. So we have actually developed methods for coronary artery disease diagnosis based on these both approaches that actually we will see. So we will also see what is flexible analytic wavelet transfer and what is the motivation. So you have a heart rate signal as input, then we perform flexible analytic wavelet transform based decomposition, and then it gives you the number of subband signals. Then we extract nonlinear features, and then all features are not useful. So we actually perform ranking of the features, and from that you find out significant feature, ranked features. Then we take select such features and give as an input to classify, and that will automatically classify normal class and coronary artery disease class. So for data acquisition and pre-processing, we have recorded these ECG signals from 10 healthy subjects and 10 coronary artery disease patients from Ekara Hospital, Calicut, Kerala, India. And this biopack equipment was used for recording such signals. And sampling rate was 500 hertz, and noise removal was actually carried out using a band pass filter whose lower cutoff frequency was 0.3 hertz and higher cutoff frequency was 15 hertz. And R peak identification was performed based on Penn-Tompkins algorithm. And total 82 heart rate variability signals we have. And so heart rate is computed by 60 upon TRR. So TRR means like this is the ECG signal, electrocardiogram signal. So you will see this is a P wave, this is Q wave, R wave, S and T. So RR interval, you measure this interval, and that is TRR. And if you divide this, compute inverse of this RR interval, that is 1 upon TRR, and then you multiply by 60. That gives you the heart rate of that particular this division. And since heart rate, when you compute this for entire ECG signal as a function of time for each beat, then this is known as heart rate variability, HRV. And that actually HRV signal we use for the diagnosis of this coronary artery disease. And we also use ECG signals, so both will be presented. So this is one of the example for this heart rate variability signals. And here you can see normal. This is the first left side normal class, and second side this is coronary artery disease CAT class. So in case of normal, you can see this heart rate actually is it is nicely actually with not fluctuating too much. But if you see in the case of coronary artery disease, your heart rate variability is actually there is a lot of variability. Now the main purpose of signal processing actually is to extract or is to quantify this kind of actually variation in the HRV due to this coronary artery disease. So that is the whole purpose of the signal analysis technique. So to define such parameter which can quantify that actually variation, which is not in the case of normal class. So that variation actually can be used as a feature together with the machine learning classifiers to identify the coronary artery disease in the initial stage. Transform, that actually it is a more general form of the wavelet transform. So in the actually previous talk we have seen like this Fourier transform has actually limitations because it is not able to represent non-steady signal, and this electrocardiogram ECG signal is also non-steady signal because their basis functions are periodic, and they are stationary basis functions their parameter don't change with time, and our signals are non-stationary, so that actually Fourier transform is not a good choice. Then short-time Fourier transform was proposed to handle non-state signals, but that also we use window function to segment the signal, and there is no thumb rule which will suggest us what should be the size of the window and what should be the type of the window. So sometimes, like in signals, actually we have different frequency component, low frequency components as well as high frequency components. Then for different frequency components, you need to have different size of the window, a different type of the window. That is actually its flexibility is not there in the STFT. So that actually done by the with the help of wavelet transform, we have that flexibility. It help us to actually it help us to find out the scale, which is actually at low scale you can have good time resolution, at large scale you can have poor time resolution, good frequency resolution. So such kind of actually multi-resolution analysis can be carried out using wavelet transform, and the conventional wavelet transform actually that we have, there also this mother wavelet is fixed. So like in HTFT we can change the different windows, types of windows, and similarly here also that mother wavelet actually can be modified with the help of parameters. So this FAWT, actually this flexible analytic wavelet transform, it is a more general form of the wavelet transform, where you have easily adjustable parameters like P, Q, R, and S, and by using these parameters you can change the Q factor of the wavelet, mother wavelet. You can change the downsampling, upsampling. So it is like it is flexible wavelet transform. And analytic word is actually the you have in the conventional wavelet transform, you have a low pass filter, and the low pass here, low pass filter actually gives you the approximation, and high pass filter gives you the details. And here, instead of one detail, you have two details. So one detail is corresponding to positive frequency, other one is corresponding to negative frequency. So in that way, this actually this gives you the analytic form, analytic arrangement of the high frequency subband signals. So due to that, we call it analytic. And now, if you see this block diagram of the wavelet, so here at each level you have one approximation, two details. And since we have actually used this flexible analytic wavelet transform for this ECG signal processing, and so that we have used it like conventional wavelet transform, but with the using this flexible property, we have actually combined these two details together, so we get one detail. So each level you have one approximation and one detail, like conventional wavelet transform, but the flexibility is you can have different mother wavelets, you can have different upsampling and downsampling like that. So now you can see the this block diagram of the flexible analytic wavelet transform, and if you use, for example, like J subbands, so like you can see, in the end you will get the approximation and the detail. So total J plus 1 subband signals will be there. One is approximation, other ones are the details. So this is one example of FAWT based decomposition for heart rate variability signal. Like we have taken third level decomposition. So we will have one approximation, three details. So A3, the approximation at the third level, and D3 the detail at third level, and detail second level. D1 is the detail at first level. So this is first case is normal, and the second side, right hand side, you see the figure that is actually coronary artery disease. So there is a lot of variability in the this subbands A3, D3, D2, D1. So we want to actually apply signal processing or analysis technique on these subbands so that we can quantify the difference between this normal and coronary artery disease. So actually, one of the important part in this differentiate that has been actually proposed the parameter selection of FAW because it's flexible. So you have to select parameters according to your requirement. So if you see the ratio of H2R greater than equals to this is actually it's the basis of FAWT basis functions shows the oscillatory nature, and in order to control the oscillations or get better time or have good time limited basis functions, the ratio of H2R must be less than 3. So for this S equal to 2 and R equals to 1, so that your ratio will be 2. So to achieve better frequency resolution, the ratio of P to Q must be like between 0.5 and 1. And here we have taken P equals to 7 and Q equals to, so ratio of P to Q is 0.875. And there is another condition that beta should be between 1 minus P to Q, this ratio, and uh, ratio of R to S. So by satisfying this condition, beta we have actually used that is 0.4. So here you can see if ratio of S to R is 3, then there is oscillatory nature of the mother wavelet, and this is not ringing effect. But when you set this ratio uh, H to R to 2, then you can see this actually there is no oscillatory effect. So this is actually a nice time limited mother wavelet. So you had it is oscillatory free. It has good resolution in time domain. So that actually by the using proper parameters we can control the mother wavelet. That flexibility was not there in the conventional wavelet transport. So features we have actually studied this k nearest neighbor KNN entropy estimator. So this is based on the distance of a sample from its kth neighbor, and it also quantify the degree of scatter. And this mathematically k nearest neighbor entropy estimator is defined by this actually d gamma function and by using this mathematical expression. And second feature that actually we have used, that is fuzzy entropy. So it is a measure of the regularity of heart rate variability time series. And fuzzy entropy mathematically it can be expressed by this mathematical expression. And where SJK is the degree of the similarity and computed using fuzzy function. And in this expression, f and g control the boundary of the fuzzy function. And we, based on the reference 10, we have used e equals to 5, f equals to 2, and g equals to 1. So in that way, this fuzzy entropy computation is carried out. And after that, this feature ranking methods, that is also very important part. So Wilcoxon method, entropy method, receiver operating characteristic method, Bhattacharya algorithm. So these actually 4 methods we have used for the feature ranking. And then least square support vector machine, that is actually improved version of the support vector machine, and that also actually we have used for the classification purpose, so that you can see mathematical expression of this LSSBM. And here sign, if it is plus then it is one class, and minus then it is another class. So kernel functions, radial basis function that actually in the LSSBM, this we have used this the mathematical expression for this RBF kernel, and Moller wavelet kernel function is also used, and whose mathematical expression also can be seen in the slide. And after that, the problem is actually how to determine the number of decomposition level, like which FAWD, which level of the decomposition should be used for the diagnosis or for this study coronary artery disease. So here you can see we have computed pre-probability values of this fuzzy entropy computed from approximation signal at second level, third level, fourth level, fifth level. And the p-value, if it is coming out less than 0.05, then we call it statistically significant. So we have selected lowest actually p-value. So third level you can see it is giving lowest p-value. So based on that we have actually selected third level of the decomposition for this developing our methodology or framework. And once you select third level, then you go for this detail, 3-level details, and third level approximation. So 4 subband signals are there, and we have computed KNN entropy and fuzzy entropy. And based on that, these are the probability values. So you can see in all cases actually, this is statistically significant. The difference is there at the level of 3. And then actually, this you can see mean and standard deviation of the computed features, KNN entropy and fuzzy entropy. So CAD class and normal class, and it is clear from this table. There's different actually these features. They cover different range for normal and CAD class for the different subband signals. And this is also clear from the box plots, which shows the range of the features for KNN entropy and fuzzy entropy. So here you can see the detail, first level detail, second level detail, third level detail, and third level approximation. In all cases, like in normal class and the coronary artery disease, both class by the feature like KNN entropy, method, fuzzy entropy, both features are able to actually discriminate these two classes at each level. So that actually, and the discrimination is not very significant, like not proper, not completely. So we actually motivate us to use classifiers. So this is actually we have this ranking number of features. They are ranked based on the Wilcoxon Bhattacharya ROC entropy based method. And for the Morlett Puplet kernel function, is the first is part, and the second part is for RBF kernel. So here you can see this number of features. If you fold, you see it is giving 100% classification accuracy for this study database. And similarly, we have seen if you use RBF kernel function, then it is significant feature number of features. If you use 4, then you get the better performance. And then actually there are many methods in the literature for this coronary artery disease detection. Lee and others 2007, they use heart rate variability, linear and nonlinear methods, and 6 linear and 5 nonlinear feature. Then you support vector machine, and they got 90% classification accuracy. Similarly, there are other authors you can see in this slide. They use EMD, TEO, integral energy operator, empirical mode decomposition, binary particle swarm optimization with different set of features, and with different machine learning algorithms like back propagation neural network, support vector machine. They got different classification accuracy. And here in this slide also recent methods you can see. And our proposed method that is based on the heart rate variability and flexible analytic probability transform, and this KNN entropy estimator and fuzzy entropy together with least square support vector machine. So it gives 100% actually for this database, and it is better than the previous one. Previous studies it was on 99.70% on the same database, and it was using TQW, tunable QWT transform. So this FAWT is more general form of the TQWT, and it is actually very useful. Even you see DWT also people have applied this GRI and 2013. So that is the conventional, then TQWT, FAWT. So it is more general form of the wavelet transform. Actually, it help us to get the good performance in the classification process. After that, actually, we have proposed this automated diagnosis method for coronary artery disease patients using ECG signals, like based on FAWT. So earlier you have seen this is based on the heart rate variability signal, HRV signals. Now we will see how this ECG signal actually can be used for the diagnosis of this coronary artery disease. So this is the proposed methodology. We have raw ECG signal, and then noise and baseline winder removal is actually performed. Then we have performed segmentation of ECG signal to reads, and then we have actually decomposed these reads using FAWT method. Then we have computed this cross information potential, actually that is from the detail coefficients, and that is very important. And luckily, actually, we have two details at each level, and both the details can be used for computing this cross information potential. And once you have this, then this part computation of CIP, then we perform classification using least square support vector machine and RBF and Morlett Puplet kernels. And then actually it classifies this ECG signal beat into two classes, uh, either CAD or normal. So in that way, this detection of the CAD can be carried out using such kind of framework. So for database, we have St. Petersburg Institute of Cardiological Techniques database is used. Also, we have used Fantasia Open Access database. So it has 40 normal subjects and 7 CAT subjects. And sampling frequency for normal EC signal is 250 samples per second. And this coronary artery disease EC signals, it is 256 samples per second. And for pre-processing, similar to previous part, this baseline wander and noise elimination has been done using UHE6 basis functional wavelet. RP detection is actually done using Point Hopkins algorithm. And ECG beat is actually segment of 169 samples. So total in this study, we have 44,426 CAD ECG beats and 1,37,587 normal ECGs. Now we have to classify them using the signal analysis technique and machine learning and framework. So this is one example. Here you can see these are the two beats. The first one is normal class and the second one is coronary artery disease. So here is due to this coronary artery disease, this beat shape is modified and that is actually now you want to this modification or abnormality in the beat want to detect using signal analysis technique or feature. So for that actually you can see we have performed this FAWT based decomposition. So here you have this first approximation there are like this is a coefficient value for the first level, second level, third, fourth and fifth. So if you are using fifth level decomposition, then actually you will have five details and each detail will have two components. So from that, this is the first part and this is the second part. So in that way, this is for normal class. Sorry, first one is for CAT class and second one is for normal class. Once you have this cross information potential, then actually, and this cross information potential is computed between the values of real coefficients and it can be estimated using based approach. Mathematical expression you can see here, and for the computation of this cross information potential, Gaussian kernel is required. So this
We will go to your office.
actually is used to estimate the cross information potential. So now we will see the results, mean and standard deviation of this cross information potential features. So level of decomposition, first, second, third, fourth, fifth, and these are the actually at each level from the two details we have computed cross information potential, and then you see this mean plus minus standard deviation along for CAT class and normal class. And then p value. So in all cases, actually p value is less than 0.05. Even in fact, it is less than 0.001. So it is a very significant difference between these two classes. And now we can see the results of classification at different levels of decomposition using different
Hello, Aman see.
So here 5 level of decomposition,
Hello.
different levels. Yes, please.
No, sir, please continue. Someone was just talking
Okay.
here.
So now at each level, we are using this kernel RBF modeled wavelet, and you can see its accuracy, sensitivity, specificity at different levels. Now we have computed this performance measures terms of accuracy, sensitivity, specificity as a number of folds, like 10-fold cross validation. So what we do actually, we divide these features into 10 sets and 9 sets we take for training and remaining for testing. And then we repeat it. So we call them fold. So each fold, you can see the performance measures. And similar, this is first one is for RBF kernel and second one is the smaller wavelet kernel. Then actually we have compared our method with the other existing method in the literature which has been issued the same database. So Acharya others in 2016 they use ECG signals and higher order statistics. and 31 cumulant features. They together with decision tree.
Hello, sir. Please unmute your mic. Hello, sir. Sir, your mic is off. Hello.
I don't know why it is muted. Now it is fine.
Yes, now it is fine. Okay, sir. Thank you.
So, could you please help me when it was muted? So I will start from that slide. From here,
Sir, from this slide.
this one only.
Yes.
Yeah, yeah. Yes.
Now it is audible.
Yes, sir.
Okay, okay.
Yes,
Thank
sir.
you. Thank you. So actually we have ECG signal, then we have pre-processed and segmented the ECG signal into beats. Then each beat is decomposed into subband signals using this affidability method. And then you have like a J level decomposition. Then you have total J plus one subband signals. Then for each
Yes, yes.
subband, we compute the sample entropy. Then we gave them as input to classification for this classifier for the classification purpose, and automatically it
Now it's okay.
classifies
Yes, yes.
in the form of
Yes, yes, we are
either
checking.
normal ECG beat or MI ECG. So in that way, this beat represents the actually person. So we can take the decision whether this person has his MI disease or not. So for this data actually acquisition, we have taken PTB diagnostic ECG database. Sampling rate is 1000 samples per second. And there are 52 normal subjects, and the myocardial infarct subjects are 148. And DVHE 6 wavelet basis function has been used like earlier for the noise removal. And PENT-MKIS algorithm is used to identify the R peaks. So now here total myocardial infection ECG beats are 40,182, and normal ECG beats are 10,546. So here you can see this is one example of this normal and myocardial infarction beats. So this first one is normal and second one is myocardial infarction MI beat, and it is distorted, and this distortion is actually taking place due to this myocardial infarction disease. So that we want to actually extract using this signal processing method. And then we have actually performed decomposition, fifth level decomposition using FAWT method. So we'll have 6 subbands, 1 approximation, 5 details. So this first one is for normal case, and second one is actually for myocardial infarction. So you can see the number of subbands. And then actually these features that we have, sample entropy that we have used, measures the complexity of the signal that for that we are computing it. And also it improve the performance by excluding the Y's due to the self matches counting the computation of approximate. So it is an improved version of the approximate entropy. And we have used random forest and least square support vector machine based classifier in this work to classify the normal and MI ECG bits. So here you can see this accuracy is plotted versus R, related parameter R, and this is number of labels also. So based on the this plot, you can see this 0.35, it is becoming higher accuracy. In that way it is selected, and this accuracy, if you increase number of labels, then actually it is also not decreasing, it is always increasing. So the best possible number, like 24 that we have selected for our study. So in that way we will have 25 subband signals. So here you can see mean standard deviation of the computed features. So like for 25 subbands, the normal class, myocardial infarction class, and that you can see these features are actually showing the different mean standard, different range. And so these features are discriminatory in nature. And then we have used classification that for unbalanced data set using least square support vector machine. So you have linear, polynomial, RBF, Morley wavelet, and these are the trial and error based selected parameters, and accuracy, sensitivity, specificity computed. And same actually for balanced data set we done using least square support vector machine. So that you can same parameters are computed based on trial and error method, and then accuracy, sensitivity, specificity you can see in this table. So we have actually compared our method with other existing methods in the literature. You can see for this database, various authors have proposed using this different classifier, different signal processing techniques. In this table you can see, and earlier method, like recent method that was proposed by Acharya others in 2017, they did not extract any features and no selection, feature selection, access selection, and they using one lead only. They use deep learning, and they got 95.22% classification accuracy. And we same database actually when we use FAWT and sample entropy, and it's only one lead. Then without deep learning, actually we reached square support vector machine with RVF kernel, and we got 99.31%. So even sometimes it is bad actually. Even the conventional machine learning approaches together with proper signal processing technique can give you the better performance. So after that, this computer-based method for the diagnosis of congestive heart failure, HRV signals using FAWT, this method has been proposed actually, that we will see. Is it audible?
Yes, sir.
Thank you.
Sir.
So this nearly 26 million people actually in the world, they are living with congestive heart failure. And in this congestive heart failure, this heart is actually not able to provide sufficient blood supply to fulfill the requirements of the body. And dyspnea, edema, and fatigue, these are the common symptoms of this congestive heart failure. And congestive heart failure patients are more susceptible to sudden cardiac death. So due to that, actually, there is a lot of motivation in the literature to develop such systems which can detect the disease in the initial level. So this is the proposed methodology. We have heart rate variability signal, and then actually we decompose this signal using FEWT method, and then it gives you a different subband signals. Then what we have suggested, adding subbands from high frequency to low frequency and adding subband from low frequency to high frequency. So in that way, actually, we have multiple frequency bands and the different resolutions, low to high and high to low. And once you have this, then we have computed this accumulated fuzzy entropy and accumulated permutation entropy that we'll see. And once you have these features, then we have ranked the features, and the ranked features are given as input to least square support vector machine for classification purpose. And in that way, this actually method classifies this heart rate variability signal in the form of either it is congestive heart failure class blocks or normal class.
Just like this.
So for this study, we have obtained RR interval directories from the FusionNet dataset, and this says congestive heart failure patient 15, and normal subjects are 40 from phaneresia and 18 from MITBH normal sinus rhythm database. So in a total, if you see the normal HRV segment we have, that is from MITBH, that is 3,420, and normal HRV segment Fantasia 500, and CH congestive heart failure HRV segments total we have 3,212. So now this congestive heart failure and normal, this class actually we want to classify using this signal processing machine learning techniques. So this here you can see this RR interval signal. So this first one is normal case, and second one is congestive heart failure. So here you can see in congestive heart failure case, this RR interval is actually looks like noisy. There is no pattern, but in the case of normal, it is changing slowly, smoothly, and there is like a correlation there. On the other hand, RR interval, it is a zigzag kind of pattern.
So shocking.
We want to detect that actually that feature using signal processing. So we have performed this FAWT based decomposition method. Here you will have like 5-level decomposition. So this first one normal subject. So you have approximation 5th level and all details and 1, 2, 3, 4, 5 level. Similarly, congestive heart failure case also you can see the 6 subband signal using FAWT method. Then we have actually the features. We have computed permutation entropy and fuzzy entropy. Fuzzy entropy already explained in the earlier section, and the mathematical expression of the permutation entropy you can see in this slide. And after that, we have actually accumulated this fuzzy entropy, the accumulated permutation entropy using the mathematical expression there that you can see. This is for accumulation fuzzy entropy. This is accumulated permutation entropy, and then actually we have done this low to high, high to low scaling. So here you can see different scales we have computed. This is a low to high, and this is high to low. So now different scales, subband signals scales, we have actually computed features, and then you can see the results accuracy in terms of percentage for the features for different kernels using the least square support vector machine classifier, and this accumulated fuzzy entropy, accumulated permutation entropy, and the sequence length linear, RVA, Morley Wavelet polynomial, and you can see this bold entry like the accumulated fuzzy entropy is the best performance, and when you use the accumulated permutation entropy, then this is the best performance, 91.39%. Then we have actually these features, accumulated fuzzy entropy, accumulated permutation entropy for these scales, low to high, high to low. You can see the features level also. So they look for normal and congestive heart failure class. They are discriminative in nature. They cover different range of the actual features. And then for unbalanced data set, balanced
What
data
about this
set,
big car?
we have actually performed the classification of based on these computed
Where?
features using ratios square support vector machine classifier. So these parameter, Morley and polynomial RBF linear converse functions have been used, and these are the parameters that are selected based on trial and error method.
Yes.
And number of features are also actually they are ranked features, and the specificity, sensitivity, accuracy
What we need
that actually you can see from the different database and different control functions together with their parameters. And then actually we have compared our method for this congestive heart failure diagnosis using heart rate variability signals. And there are various methods people have proposed in the literature: time and frequency domain based parameters, DFA based parameters. That is actually this is time frequency domain parameters, and non-linear parameters and wavelet based measures, EM empirical mode decomposition, this 13 non-linear parameters, FAWT based accumulated entropies. So this is our proposed method, and that actually together with least square support vector machine classified, it actually with the different number of features for different and this is first one unbalanced data set, and this is second, third or fourth is balanced data set. So different even all scenarios you can see we get the better performance than the other existing methods in the literature. After that, actually we have proposed this computer-aided methodology for the identification of normal and atrial fibrillation ECG signals using the signal processing machine learning technique. So this atrial fibrillation is characterized by the irregularity of atria contraction, and the number of people which have actually atrial fibrillation is double in the last 40 years. And the death of the rate for atrial fibrillation patient is double as compared to the normal subjects. And dyspnea and fatigue are common symptoms, and this electrocardiogram and ECG signal is widely used for the diagnosis of this atrial fibrillation. So this is a proposed methodology for the automated detection of this atrial fibrillation. So ECG signal, then we perform pre-processing, then we extract the small segments from ECG signal, we decompose them using FAWT method, then we compute this permutation entropy and log energy entropy. Then we perform classification using machine learning, and then it will give you normal and atrial fibrillation detection. So for database, we have used MIT BIH atrial fibrillation database, which has 23 atrial fibrillations of patients, and its sampling rate is 250 samples per second. So we have total similar to previous, we have divided 6 wavelet basis function used for noise removal, and 77,267 atrial fibrillation ECG segments, and 1,14,214 normal ECG segments. Now we have to classify them using this FAWT and machine learning. So this is an example. You can see first one is normal class ECG signal, second one is atrial fibrillation signal, and then we have decomposed this using this FAWT method. So we have used 5-level decompositions. There are 6 subbands. And then we have computed log energy, entropy, and permutation entropy features. So already permutation entropy features have been seen in the previous slides. And so log energy entropy is a mathematical expression. And then here you can see mean standard deviation values of the log energy entropy and permutation entropy features. And for this, all 6 subbands for this, and these features are discriminate in nature. And then log energy entropy, permutation entropy at different level of decompositions shows that this table shows the total number of features, and then obtained accuracy, sensitivity, specific in terms of percentage. Then we have actually we have used the earlier. Here we have used random forest classifier. Here this is
Before you join,
decision tree classifier at various decomposition levels, and that you can see using these features: log energy, entropy, permutation entropy, and different levels, total features, accuracy, sensitivity,
it was very
specificity.
tough for me.
And then actually we have combined this RF and DT classifiers at various decomposition levels with the combination of these pieces. So earlier we have studied different pieces separately. Now we have combined them. So if you see random forest classifier, decision tree classifier, different level of decomposition, total feature, then this table shows the obtained accuracy, sensitivity, specificity. And then actually you can see in this plot, we have shown the tenfold cross variation at different poles using random forest classifier and this J48 this classifier, decision tree classifier, and this random forest is giving better performance than the decision tree classifier.
Now,
Then we have compared our method with other existing methods in the literature. You can see people have used on the same database. Various researchers use various signal processing machine learning techniques, and we have actually used this ECG signal, log energy entropy and permutation entropy
during the time
features, and we are getting better accuracy
it was just introduction.
than other existing methods in the literature. So this is the conclusion of this entire talk. FAWT based automated detection method for coronary artery disease is developed using heart rate variability signals. And automated diagnosis method for coronary artery disease has been proposed based on the ECG signals. So according to requirement, we can use any one of them. And method for automated identification of myocardial infarction ECG signal based on the FAWT has been proposed. And these all methods actually they achieve better performance in terms of classification of normal and abnormal classes as compared to the reported works in the literature. And we have also seen this computer-based approach for the automated diagnosis of congestive heart failure patients developed, and our proposed method has provided better performance than the other methods in the literature. And in last part, we have seen this computer-aided identification method for atrial fibrillation ECG signals based on the FAWT, and the performance of the proposed method is actually comparable to the other methods. And it should be noted that whatever method we have proposed, it doesn't require any RP detection, PW detection, and directly it works on the signal. So this is actually these are the advantages. So this actually this work whatever I have presented in this talk, this is based on these 5 publications. So I request all the participants please go through these papers in order to understand whatever I have presented. And this is actually here FAWT method has been studied for this set of problems. You can try some other signal processing techniques also for your research, and you can try other machine learning techniques also. So there is a lot of actually directions of the research which actually can be taken up based on this presentation. So thank you very much.
So, it's over.
Thank you, sir.
Thank you very much, sir.
Achila, please ask participants and take up questions from the chat box.
There is a question in the chat box. We already have accuracy, sensitivity, etc. What does tenfold validation tell us? Professor Pachori, there is a question from the participant.
So, we already have accuracy, sensitivity. I can see in the chat box. What does 10-fold validation tell us? So actually, this 10-fold cross validation means like what we do, we divide this data features, whatever features you have obtained into 10 parts, and out of 10, we take 9 parts for the training, remaining 1 for the testing purpose. And that's we repeat 10 times. So different possible different combinations. Next time you will take other 9 sets as a training, remaining for the testing purpose. So in that way we do that entire process. That is 10-fold cross validation. It can be 5 also. If you 5 cross validation, then you can divide it into 5 parts. Will the accuracy or F1 score, which one is better as the evaluation matrix? Actually, we use various evaluation methods in order to have reliable performance, like F1 score, accuracy, sensitivity, specificity. These all are actually well known in the like just based on the true positive, true negative, all these things like whatever you want to detect. These are well known measures, and if you use more number of measures, then it is a more reliable actually performance measure. So every actually performance measure gives you the performance measure in different way. So if you have all ways, actually the possible ways to measure performance, it is how we can do sensitivity analysis. So this accuracy, sensitivity, specificity, sensitivity. This actually there is that this. Please go through these papers. Whatever I have this presented, I have last slide. In all the papers, these all these parameters have been used, and you will understand how to do score like like for example coronary artery disease, how to do sensitivity analysis, how to do this for myocardial infarction, congestive heart failure. So different scenarios is all actually these are very basic parameters, and this is what simple formulas are there. Any other questions?
Few have raised their hands. Yes, sir. Few have raised their hands. If they have
Yeah,
any question, please,
yeah, please.
you can ask.
Please keep some videos ready. Another problem.
Someone has. So no question from participant side.
Yeah.
No question. Okay. I believe there is no question from the participants. Sir, I have one question. Only one. Sir, you have developed automated computational techniques
Yes.
for all these problems, and also it is very essential that will assist the doctors. But have you implemented in any hospital or in any healthcare center and tested your models?
Yeah, actually, this whatever methods we have shown, this actually we have compared with the other existing methods in the literature which have been studied in the same database. So these are publicly available databases for research purpose. But actually,
Sir,
this is our previous work. Now we are actually even like we are designing this. Monitor actually vital sign monitors where this ECG signals, PPG signals, all the blood pressure, a lot of information actually is collected from the hospital.
yes,
We are recording from the hospitals, and we are using this IoT signal processing, machine learning to develop that
yes, you
intelligent
can,
system. So this is just
the
an
whole system can,
initial work we did,
yes,
but
sir.
now we are developing this method based on the hospitals, this hospital data.
Okay, sir. So it's a nice job, wonderful presentation. Thank you, sir, for accepting our invitation. And you delivered two lectures, and both the lectures were so insightful. And I believe all the participants who are working particularly in this area will must have got lot of information, and definitely they will do a very good work in their own field. And if any one of you needs Professor Pachori's help, please be in touch with him. And with this, I would like to thank again, sir. Thank you so much.
I will actually send my presentations to you, and please, madam, share with
Thank,
the student
sure,
participants.
sir.
Thank you very
Yes,
much for this opportunity. Thank you.
sir. Thank you.